Okay, I will start recording first.
Okay, cool.
Recording in progress.
Okay, welcome everyone. So it's a great pleasure to have Ray Wen from University of British Columbia to tell us about his recent work. Ray is a PhD student working with Andrew Porter. So I think so far Ray has done a lot of interesting work, in particular in some interdisciplinary areas like topological holography, generalized symmetry, quantum information, quantum many-body dynamics. And today he's telling us about something that may be more experimentally relevant related to MoTe materials. Ray, go ahead.
Thanks very much for the introduction. So I want to thank everyone for joining and thank Liu Jun for offering this wonderful opportunity. My topic today is topological quantum memory from gap boundaries in twisted monopodal diteloride. So this is a work based on this archive number done in joint with Andrew Porter. So this is the outline of my talk. So I will start by reviewing some basics of series and experiments of twisted TMD materials. Then I will very briefly review the proposed candidate orders in this in twisted monopodal ditelorides. Then I will review the theory of gap boundary of non-chiral topological orders and its relationship to anion condensation. So after that, I will present a classification of gap boundaries and topological defects in the candidate orders in twisted monopodal diteloride. So finally, I will discuss the detection and application of the gap boundaries in twisted monopodal ditelorides. Okay, so first of all, allow me to briefly review the band structure and symmetry of twisted TMD materials. So here I'm showing the band structure of one of the monolayer TMD material. So there are some very important properties of the band structure. So we have a very strong spin-orbit coupling, which splits the spin degeneracy, as you can see here at the K point. So the dotted red line is the band without spin-orbit coupling. And after introducing spin-orbit coupling, the band splits into two. And the valence band maxima is at the K and K prime value, and with the spins pointing up and down, respectively. So this is known as spin value locking. So essentially the electrons at the K value are pointing up, and the electrons at the K prime value are pointing down. So the system has symmetry, charge conservation, and spin rotation symmetry, and time reversal symmetry. So it's an insulator with a spin conservation symmetry and time reversal symmetry.
Just a second. I think here the symmetry, strictly speaking, the symmetry group is not this one, right? For example, time reversal squares to -1, so it's not Z2T but Z4T.
Yes, so that is correct. So electrons are chromostabilic in the sense that the T square is -1. So here the 2T means acting on bosons. I should be more precise. So acting on like excitons or Cooper pairs, then it's Z2. So technically it should be Z40. And also, yes, yeah, you're right. So technically it should be Z40. Okay, so if we consider a twisted bilayer TMD material, then we have this very interesting MoTe band structure shown here. So this is for the K value band. So the first two MoTe bands have Chern number -1 and +1. And so they have spin pointing up, right? So we have the Chern number being +1 and -1 for the K prime value. So we have these spin contrasting Chern bands with almost ideal quantum geometry in the sense that the bands are flat and the distribution of Berry curvature or quantum metric is roughly even. And so if we tune our chemical potential to be between the first and second MoTe band, we have a anomalous quantum spin Hall insulator. So basically means we have Chern number 1 for the K value and -1 for the K prime value. And so at the edge of the system, we should have counterpropagating edge modes with different spin numbers. And so if we partially fill the Chern band, we can expect a fractional quantum spin Hall state to emerge if the symmetries are still preserved. So indeed, that's what the recent experiments suggest. So recently, experiments have shown that at half filling, so here the filling is with respect to the topmost unfilled band. So the total filling may not be 1/2, but for the topmost unfilled band, the filling fraction is 1/2. And in 2.1 degree twisted molybdenum diteloride, it was observed that the system has vanishing charge Hall conductance, and they quantize the spin Hall conductivity of value 1/2. So here is a picture taken from the experiment paper. So as you can see, so here, so the relevant plateau is here. So as you can see, the Hall response is 0, Rxy here is 0, but the two-terminal resistance is non-zero, and it takes this value. So this is the two-terminal resistance, which means the spin Hall conductivity for each spin Hall conductivity would be 3/2. So here also the 1/2 here only refers to the fractional part of the actual spin Hall conductivity. So in reality, in experiments, it was observed to have 3/2 spin Hall conductivity. And similarly, this is a two-terminal conductance, and so the relevant plateau is here. So for total Fielding fraction 3, which means the Fielding fraction for each value is 3/2, and the conductance is 3 for the two-terminal conductance, which means the spin Hall conductivity would be 3/2. So this signature suggests that we're looking at a state that is a fractional insulating state with symmetry, charge conservation, spin rotation symmetry, and time reversal symmetry. So by definition, that's a fractional spin Hall state.
Yeah.
So anyone has a question?
Can you explain again what's the relation between this quantized spin Hall conductivity being 1/2 and then there's the 2/3? What's the relation?
Three.
So on the slide you said the spin Hall conductivity is 1/2, but in the picture you also said there's some 2/3.
Oh, okay. 3/2. There's no 2/3. 3/2. So the plateau here has two-terminal conductance 3.
I see.
Which means the spin Hall conductivity is 3/2. But so the fractional part is 1/2. So we're only focusing on the fractional part. Okay. So then it was proposed that there are several topological orders with this symmetry that's compatible with this signature by the work of Chaoming-Jie and MoTe2 and Tengke Xu. So first of all, so by definition, the fractional quantum spin Hall state is a symmetry enriched topological order. So the relevant symmetry here is 2 flavors of U1 symmetry and a time reversal symmetry that exchanges these 2 U1 symmetry. So these 2 U1 symmetries are reorganization of the U1 charge and U1 spin here. So basically, you can view the electrons in the K valley and K prime valley as separately conserved. And so then the time reversal symmetry just exchanges the K and K prime valley. So among the candidate orders, there is one family of orders called we call helical orders. So they take the form of S times S bar. So S can be any insulating state at half-field lambda level, and S bar is the time reversal conjugate. And so combined, they can match with the transport data measured in experiments. So the reason is that so we have this Maury band with turn number 1 or -1 with almost ideal quantum geometry, which means that they can basically be viewed as lowest lambda level. So if we have viewed these lambda levels, then we know that there are many candidate insulating states S. So if we take any of these insulating states and then take the time reversal conjugate and then take the product, we would have a state that has this symmetry, and it would have a 0 Hall conductance, but 1/2 spin Hall conductance, which would match with the transport data. So the candidate state for S, for the basically for the spin up degrees of freedom, can be any one of the following. It can be U1 level 8, or it can be Fathian state, which is Ising times U1 level 8 over J2. So I will talk a little bit more about this over J2 operation later. So, and it can also be particle Hall Fathian, which is Ising bar, the time reversal conjugate of Ising times U1 level 8 over J2. And so if we label so as you can see that for all these candidate orders, the spin up part, that is the S state here, there is always this U1 level 8 sector, right? So if we label the anyons from the U1 level 8 sector as an integer n ranging from 0 to 7, and so we have 2 integers, one for the U1 level 8 in the spin up sector, and then one for the U1 minus 8 for the spin down sector. So we can call these 2 integers n up and n down. Then the charge and spin of anyons are related to n up and n down in this way. So the charge and spin here are given in units of electron charge and electron spin. And so you can say that, so in this system, so the minimal charge is 1/4 and the minimal spin is 1/4. And so this fractional charges and fractional spin can give you the correct spin Hall conductance, that is 1/2. Okay, so these are the helical orders. It is also possible to have a non-helical order, which is a valid entangled state. So this is the Z4 topological order, or also known as the Tori code in the quantum information community. So this order can be viewed in computer study in many ways. So you can either view this as a quantum disordered intervallic coherent state. That is, you first go to a intervallic coherent state by breaking the spin conservation symmetry, and then you can consider proliferating the 8-pi vortex, which would restore the symmetry. And since the 8-pi vortex is 4 times 2 pi, you end up with a Z4 topological order. You can also achieve the Z4 order by condensing intervallic exciton and a Kupler pair with certain flux attachment, as described in this work. And lastly, you can also view this Z4 order as resulting from anion condensation of the helical states. That is, if you take any one of the helical states that I discussed earlier, and there is certain anion condensation you can do in this helical order, which would result in this Z4 order. And it was also shown in this work by Chaoming-Jie, MoTe2, and Chen Ke-Xu that Z4 order is a minimal order compatible with the transport data, which means that this is the smallest topological order that has the correct charge and spin Hall conductance. So allow me to summarize some of the key properties of the Z4 order here. So this Z4 order are generated, the anions in this Z4 order are generated by two fundamental anions, E and M. So they are order 4, and they are both bosons, and they have mutual I statistics. So there will be in total 16 anions. And the charge and spin of anions in this system are given as follows. So the E particle has half of an electron charge and has 0 spin, and the M particle has no charge and half spin. So you can say that this is very different from the helical orders, because in any of these helical orders, there are anions with 1/4 charge and 1/4 spin. But in this this valid entangled state, there is only 1/2 charged particles and half spin particles. Okay, so what is common about all these candidate states is that they are all non-chiral. Of course, this is because the system has 0 net Hall conductivity. And so, but this also means that it is actually possible to have gap boundaries for these orders. So currently, although the current experiments have only found the counter-propagating edge modes, right, the gapless non-chiral edge modes, but it was also observed that we can suppress the edge conductance by introducing in-plane magnetic field, shown in this figure. So in principle, if the in-plane magnetic field is strong enough, it is possible to completely gap out the edge. So this is unique to these non-chiral topological orders, because in a chiral topological order, like in a fractional on the Hall state, the edge mode is robust, right? And as long as the bulk gap is not closed, then you can never gap out the boundary. But for this fractional quantum spin Hall state, it is actually possible to introduce gap boundaries. So this is very interesting because topological order with gap boundaries can be used for topological quantum error correcting code. So, for example, the famous surface code consists of the simplest non-chiral topological order, the Z2 order, with 2 types of gap boundaries. And so what's nice about this architecture is that we do not need any non-Abelian anions like Majorana or parafermions. And it is in principle possible to achieve universal quantum computation within pure Abelian topological orders if it's non-chiral. So that's the motivation of this work, that is to classify and characterize the gap boundaries and the topological defects in all of these candidate fractional quantum spin Hall orders, and then to design schemes for detecting and measuring the topological degeneracy associated with these gap boundaries. So let me take the Z4 order as an example. So I will discuss the gap boundaries of the Z4 order and their relation to anion condensations. So the bulk of the Z4 order can be described by a mutual Chern-Simons term given by the term here. So for this theory, so for this bulk Chern-Simons theory, we have 2 U1 gauge fields corresponding to the anion E and M, So they are also dual to the intervalley exciton and Cooper pair current. So this mutual Chern-Simons term encodes the mutual I statistics between the E and M particle. And these AS and AC gauge fields are the background gauge field for the two U1 symmetries, and they couple with the AE and the E and M particles with coefficient 2. And so starting from this box theory, we can go to the boundary Luttinger liquid theory. So the first two terms are the topological part of the Luttinger liquid, and the last part is a density-density interaction term with an interaction matrix and a coefficient base that is not topological and not universal. So from the symmetry action on the anions DIM, or from the symmetry action on the exciton and Cooper pair, we can read off the symmetry action on these Luttinger liquid fields. So phi E is a half charge and phi M is a half spin. And time reversal symmetry leaves the E particle invariant and maps M to its time reversal conjugate. And this pi over 4 shift encodes the fact that M squared is a Cramer's doublet. So this is the Lagrangian theory for the boundary of this default order. So as written here, it is a gapless theory with a pair of counter-propagating gapless modes, right? So this is a gapless. This is a theory for a gapless boundary. But so actually, it is actually possible to gap out this boundary by introducing superconductivity. So for instance, if we can consider this superconducting term on the boundary, which condenses the intervalley Cooper pair, and if we go to the Bose-Nash divergence, and this actually becomes the cosine term for the phi E field for the E particle. And so this term essentially, when the coefficient lambda s is large enough, pins the phi E field to one of the 4 minima, right? And so once the phi E field is pinned, then the anion creation operator for the E particle will acquire an expectation value. So this can be understood from an anion condensation picture. So essentially at this boundary, at this superconducting boundary, the E anion is condensed and the charge conservation is broken because the E particle carries half charge. And the spin rotation and time reversal symmetry is preserved because the E particle has trivial U1S and T symmetry action. So this relationship. Go ahead.
Yeah, excuse me, I'm a bit confused here. So, is this U1C and U1S here correspond to the global symmetry in the symmetry enriched topological order?
Yes. So this is a symmetry enriched topological order. So the anions are generate the default order, and so the symmetry enriching is encoded by the charges. So the charges of U1C and U1S of the anion. So the E particle has so I think so as reviewed here. So the E anion has half charge and no spin, which means if you do a 2 pi rotation like of the U1 charge symmetry, you get a -1. And for the M particle, it's a half spin. So these data encode the symmetry enrichment of the topological order.
Oh, I see. So this
U1. Sorry, you go ahead.
Thanks.
You go ahead. Sorry.
Yeah, thanks. So this U1 background gauge field is not the global symmetry.
It is a background gauge field for the global symmetry. It's not gauged. So okay. So for the Lagrangian here, only the little a's, AE and AM, are dynamic gauge field, and its capital AS and AC are background gauge field.
I see.
Yes.
Thanks.
So yeah. So maybe just to summarize here. So basically, the first term describes the topological order, and the last two terms describe the symmetry enrichment of the topological order. And so in the anion condensation picture, so the superconducting boundary has the E anion condensed, and the charge conservation is broken because the E anion carries half charge, but the E anion has trivial spin and the time reversal action. So the spin rotation and time reversal symmetry remains unbroken. So this relationship between gap boundaries of abelian topological order and anion condensation is actually general. So it was shown in a work by Meisen, Berkshire, and Changming and Xiaoliang that gap boundaries of any abelian topological order are in 1-1 correspondence with Lagrangian subgroups. So Lagrangian subgroups essentially describes condensation of bosonic anions that completely trivializes topological order. So for instance, for this previous example, the E anion is condensed, And then the M anion is actually confined because it has non-trivial braiding with the E anion. So if we move the anions from the bulk to the boundary, then the anion is either condensed at the boundary or it's confined at the boundary. So no non-trivial anions stay deconfined at the boundary. So this is generally true. So any gap boundary is described by a condensation of bosonic anions that trivializes the topological order. So for this, the four order is actually quite simple. We can completely enumerate all the Lagrangian subgroups, and turns out there are three of them. So one is condensing the E anion, the other is condensing the M anion. There's also a third one that condenses the E square and M square anion. So E square and M square are both bosons, and they can actually be condensed simultaneously because they break trivially. And we have seen that the E condensed boundary corresponds to a superconducting boundary. Then next, I want to show you what's the interpretation of the other two choices. So for the Lagrangian subgroup generated by M, it's actually an intervalley coherence boundary with broken spin rotation symmetry. So if we consider a intervalley coherence Hamiltonian as a boundary, which condenses the exciton in a system, and then if we go to the Bose-Nash picture, this actually becomes a cosine for the phi n field. And so, which means if the coefficient is large enough, this phi n field would be pinned to one of the four minima. And so this effectively condenses the anion M at the boundary. So this is kind of a dual to the E condensed boundary. This condenses the M particle at the boundary. And since M particle has non-trivial spin and time reversal symmetry action, so at this M condensed boundary, both U1s and T are broken. And so there's also a third choice that is a Lagrangian subgroup generated by E squared and M squared. So this is a boundary that is both intervalley coherence and also superconducting. So this condensation pins the field 2 phi E and 2 phi M. So phi E and phi M are not mutually local, so they cannot be pinned to given value, but 2 phi E and 2 phi M can actually be pinned to a fixed value. And so this boundary breaks all the symmetry. So in summary, by enumerating the anion condensations in the day 4 order, we can enumerate all the possible gap boundaries of the day 4 order, and they can be distinguished by their anion condensation pattern or by their symmetry pattern. So they have different symmetries on the boundary. So we can actually make use of this to build a topologically protected qudit.
Question? Can you go back? I'm a bit confused. So E carries charge 1/2.
Yes.
And then if I condense E squared and M squared, M doesn't carry charge.
Yes.
If I condense E squared, why is it a superconducting boundary?
Because E squared, it does not have fractional charge, but it has integer charge. So it still breaks the U1 charge conservation symmetry.
But E squared is not a local object. If I ask what is the order parameter on the boundary, what's the local order parameter corresponding to the superconducting order? What is it?
It's still the same. Okay, so it is still the same order parameter, like for the E condensed boundary. It is the same, but not both the IVC order parameter and the superconducting order parameter are non-trivial. They have expectation value. So E squared does not have fractional charge, but it has charge 1.
Yeah, so E to the I phi E is the boundary field for E. So do you mean E to the I 4 phi E is the boundary order parameter?
Yes, that is correct. So this order parameter, so this is order parameter for both E or E squared because E squared is also non-local. E is also non-local. So the local order parameter is still E to the I 4 phi E, but this is induced by condensing the non-local object E or E squared.
Yeah, but this object carries charge 2E, right? Then in principle,
the order parameter is always E to the I phi E and 4 phi E. So the phi E to the I 4 phi E.
That carries charge 2E. So when I condense it, is it possible that E to the I 4 phi E is always bonded with a Cooper pair of electrons. I guess, well, yeah, I think I think it just is the Cooper pair of the electrons.
Yes, E is. I think 4e is e to the fourth power is the same as the Cooper pair.
Yeah. Okay, thanks.
Yes. Yeah. Okay. Yeah. Similarly, m to the fourth power is the same as exciton. Okay. So we can actually make use of this gap boundaries to make a topologically projected qudit. So this is a Z4 version. So if we assume that this fractional quantum spin Hall state is a Z4 order, and then so if we just drill a hole in this twisted molybdenum ditelluride and we gap out the inner and outer boundaries by introducing superconductivity, for instance, by using the proximity effect, and then the system actually has fourfold topologically protected ground state degeneracy, because since if the inner and outer boundaries are superconducting, as we discussed earlier, the E particle is condensed. So tunneling an E particle from the inner boundary to the outer boundary is a zero mode. Actually, it preserves the ground space. So similarly, there is another zero mode that's moving an M particle around this hole. So these operations do not commute. They commute up to a phase I. So this protects a fourfold ground state degeneracy. And so this is topological in the sense that as long as the inner and outer boundaries stay gapped, then there is always a fourfold ground state degeneracy. And if we have n of these superconducting holes, the ground state degeneracy would be 4 to the power of n. So we would like to generalize this to the gap boundaries of other fractional quantum spin Hall states. So before I do that, allow me to briefly discuss the Bach boundary correspondence for non-chiral topological orders. So for chiral topological order, we understand the Bach boundary correspondence states that the chirality of the edge mode is topologically invariant. There is also a Bach boundary correspondence for non-chiral orders. So for non-chiral topological orders, it is possible to have gap boundaries, and the gap boundaries are in one-one correspondence with trivializing anion condensations, a fact proven by Liang Kong, Xiaogang Wu, and Haojun in this work. So here are some mathematical details. So a topological order is described by a unitary modular category. So, or in the case of a fermionic topological order, is described by a unitary supermodular category. And a trivializing anion condensation is described by a Lagrangian algebra, which is a non-Abelian generalization of Lagrangian subgroup. So for Abelian topological order, we can work with Lagrangian subgroups. But in general, for a non-Abelian order, anion condensation is described by condensable algebras, and trivializing anion condensation is described by Lagrangian algebras. And there is also a subtlety with fermionic topological order. That is, it is actually possible to condense objects like Fc, where F is a fermionic anion and C is a physical fermion. So this whole thing, this composite particle is still bosonic, but the anion part, F, is fermion. So this is beyond the description of Lagrangian algebra, because Lagrangian algebra only describes the condensation of bosonic anions. So, but for fermionic topological order, essentially, it is possible to condense fermionic anions. So there are two common solutions. That is, we can either work with a modular extension, or we can work with Lagrangian superalgebra. So Lagrangian superalgebra basically allows condensation of fermionic anions, and a modular extension is essentially obtained by gauging fermion parity in this fermionic topological order to get a bosonic topological order, and then we can study a usual Lagrangian algebra in bosonic topological order. So this can be summarized in this diagram. So again, gap boundaries of non-chiral topological order corresponds to Lagrangian condensation. So if we started with a fermionic topological order here, and we want to study an anion condensation, so which may include condensation of fermions, because this is a fermionic topological order. So this will be described by a Lagrangian superalgebra, and we end up with, so if the algebra is AF, we end up with a smaller, in some sense, a smaller topological order, denoted by this quotient by AF. But we can also do this in a different way. That is, we can first gauge the fermion parity in this fermionic topological order to go to the so-called modular extension, which is the bosonic topological order. And starting with this bosonic topological order, we can do a usual anion condensation, that is a boson condensation, and which is described by Lagrangian algebra. And then we end up with this topological order, and we can undo the modular extension by doing something called fermion condensation. So, okay, this may seem very formal, but as an example, for one of these helical fractional quantum spin Hall state, Pfaffian times anti-Pfaffian, if we gauge the fermion parity, a modular extension is given by Ising times U1 level 8 times Ising bar times U1 level -8. And so we can recover the Pfaffian times anti-Pfaffian by condensing these two anions, these two objects. These are actually not just anions. So the psi4 is, we call the notation, so psi is the anion in the Ising sector. So psi is the anion in the Ising sector, and this 4 is anion in the U1 level 8 sector. And so psi4 bar, so psi bar is an anion in the Ising sector, and this subscript 4 is an anion in the U1 -8 sector. So C is the physical fermion. So if we condense these two composite particles, then we can recover the Pfaffian times the anti-Pfaffian. So what we will do is to basically use the red path instead of the blue path. Okay, so here is the here. So allow me to present the classification of the gap boundaries of the other fractional quantum spin Hall states. So as an example, let us look at the Pfaffian times anti-Pfaffian state. Again, so a modular extension is so this is the bosonic topological order. And so here I summarize some of the basic properties of the Ising topological order and U1 level 8 topological order. So for the Ising, there are 3 anions labeled by 1 sigma and phi. And the fusion rule is that sigma square is 1 plus phi, 1 plus psi, and psi square is 1, and sigma times psi equals sigma. And so here are the spin and braiding of the anions in the Ising topological order. So the sigma particle has the non-trivial spin, e to the I pi over 8, and the psi particle is a fermion, and they have mutual -1 braiding. And for the U1 level 8 topological order, so the anions can be labeled by an integer ranging from 0 to 7, and the fusion rule is just addition of integers mod 8. And so the spin and braiding are given as follows. So the n particle has spin e to the I pi n square over 8, and the mutual braiding between the n particle and an m particle is e to the 2 pi I n m over 8. So let me introduce a notation that is very convenient. That is, we can denote an anion in Ising times U1 level 8 as A with the subscript n. So where A can be A is 1 sigma phi psi coming from the Ising sector, and the n is coming from the U1 level 8 sector. So a general anion in the Ising times U1 level 8 times Ising bar times U1 -8 can be labeled as A n and B bar m. So B bar comes from the Ising bar sector, can be 1 bar or psi bar or sigma bar, and m comes from the U1 -8 sector. It can be any integer from 0 to 7. And again, we can recover the Pfaffian times anti-Pfaffian by doing this fermion condensation. So fermion condensation in the sense that the anion part, psi4 and psi4 bar, are fermions. Okay, so here is the strategy of classifying Lagrangian condensations, which means classification of gap boundaries for this Pfaffian times anti-Pfaffian order. So we show that, first of all, we show that any Lagrangian condensation in Pfaffian times anti-Pfaffian must condense anion 1,4 and 1,4 bar. So which means this is an anion that's coming from purely the U1 level 8 sector and the U1 level -8 sector. And so this is a boson, and it has, as you can check, it has a spin 1 and the charge 1. And it has order 2. And so this is the first lemma. So, and then if we condense this anion in the Pfaffian times anti-Pfaffian, it will reduce the topological order to a Z4 order. And so if we combine these two facts, we see that there are only 3 Lagrangian condensations in Pfaffian times anti-Pfaffian. So if you want to do any Lagrangian condensation in Pfaffian times anti-Pfaffian, we must first condense the 1,4,1,4 bar anion. And this will reduce the topological order to Z4. And then we have already showed that for Z4 order, there are only 3 boundaries. So this completes the proof that for the Pfaffian times anti-Pfaffian, there are only 3 boundaries, gap boundaries. And they have different symmetries, right? And they have different anion condensation patterns. Okay, so
yeah, just to make sure, I thought previously when you reviewed the previous work, you said it was known from some previous paper, starting from Pfaffian times anti-Pfaffian, we can get Z4 topological order?
So I think this has not been shown explicitly. It has been argued. I think it has been argued that you can get Z4 from Pfaffian times anti-Pfaffian. But okay, but what is important is that this is not only a possibility, but it's inevitable, which means that any Lagrangian or any trivializing condensation must condense this anion. So it must go to Z4. There is no other option. And this is important because So without this fact, it may go to some other order, and then so you don't know what happens. So, but this basically shows that there's only one option. If you want to do a trivializing condensation, you must condense this specific anion, and then you end up with the full order.
Okay, thank you.
Nice.
Oh, excuse me.
Yeah. Sure. Go ahead.
Please go back to the previous slide. Yeah. So here the argument is that you said that this Pfaffian times Pfaffian bar has 3 gap boundaries because of the diagram. Is it correct?
Yes. Yes.
But for example, let's think about the Ising times Ising bar, which is just an example. So you can condense the psi bar in Ising times Ising bar, and you will get C2 toroid code. Then C2 toroid code has 2 boundaries.
Yes.
But Ising times Ising bar has only 1 boundary, because if you write down these 2 different kind of boundaries in a specific model, then you will find that they are Morita equivalent.
I see. So you are saying, so for Ising times Ising bar, if I first do a psi bar condensation and go to toric code, so it would appear that we have 2 boundaries, but they are actually equivalent. So that is correct. Yes. I agree that for Ising bar, there is only 1 gap boundary. But here, actually, so there's a simple checks because they have different symmetries, so they cannot be equivalent.
I see.
Yes, yeah. Or actually, so you can actually you can write down the complete condensable algebra. Like you can combine these 2 paths, and you can write down the full condensable algebra, and you can show that they are equivalent.
I see. Thanks.
Yeah, that's a good question. So, so in general, so basically, diagrams like this does not guarantee you that all these boundaries are distinct. But in this case, you can easily check that they are distinct because they have different symmetries, or you can just write down the complete condensation, and you can say that the anions that are condensed are different. So yes, so essentially, so here is some details of showing that condensing 1,4,1,4 bar in
I'm sorry.
I think gives.
Sorry, another question, but also related to the diagram. So, how do you guarantee that we have only at most 3 boundaries here? I think yeah.
So I think that's what this first lemma says. So any Lagrangian condensation must condense this anion. So so it reduces to the 4 order, and for the 4 order there are only 3. So we have at most 3 boundaries. Gap boundaries. So this first one is I will not present the proof of this first one in this talk, but basically you can enumerate all the bosons in the theory.
Yeah.
And so you can find details in the appendix of our work. But this basically guarantees that there are no other gap boundaries, because you always have to condense this anion in a Lagrangian one, in a Lagrangian condensation, and Lagrangian is very important here.
I see. Okay, thank you.
Okay, so here are some details of this of the second lemma. So the fact that if you condense 1,4,1,4 bar, you end up with the 4 order. So it is important to notice that this psi4 bar anion in the Pfaffian times Pfaffian is actually identified with vacuum, because in each factor in Pfaffian, for example, psi4 is identified with the physical fermion, and in Pfaffian bar, psi4 bar is identified with the physical fermion, which means this is identified with the vacuum. Or Cooper pair, you can say it's Cooper pair, but Cooper pair topologically is the same as vacuum. So topologically this is trivial, and which means if we condense 1,4,1,4 bar, we also condense the psi bar. So we can consider essentially condensation in the Ising times Ising bar sector and the U1 level A times U1 minus A sector. So in the Ising times Ising bar sector, as pointed out by the audience, that if you condense psi bar, you end up with a Z2 order. This is first shown in the Bice and the Slingerland's work. And so for the U1 level A times U1 minus A, this is a Abelian topological order. So it's relatively simple. You can work out the condensation, and you say that you end up with a Z4 order. So if you combine these two, we end up with a Z2 times Z4 order, but we need to undo the modular extension, which will quotient the topological order by another Z2. So we end up with a Z4 order times the physical fermion C. Okay, so what is interesting is that so this is actually true.
Another question. Yeah. So for the last line, why do we know that this is a Z4, not a Z2 times Z2?
Okay. Yeah. So in principle, you're right. Just from this expression, it appears we can have Z2 times Z2, but the actual computation shows that it is Z4 because the psi4 anion is actually generating anion for the Z2 order, and that's essentially condensed. So you get rid of the Z2 part, and you only have the Z4 part. Yeah, you can find the computation of this in our work. Yeah, it's a very good question.
I see.
So turns out this is true in all of the helical orders. So we basically similarly we have these two lemmas. So any Lagrangian condensation in any of these helical orders must condense an order 2 abelian anion. It's called a Z, and this anion corresponds to threading 4-pi flux in both valleys, which means by the Hall response, this anion Z will have charge 1 and spin 1. And so it is an abelian boson with order 2. And if we condense this anion Z, it will reduce the helical order to the Z4 order. So we have this following diagram. So this gives us this conclusion that all the candidate orders compatible with the transport data have exactly 3 types of gap boundaries distinguished by their anion condensation and symmetry breaking patterns. So essentially, for all the possible fractional quantum spin Hall states compatible with the transport data, you can either have a superconducting boundary, a intervallic coherence boundary, or a boundary that breaks all the symmetry.
So here the transport data means the charge Hall being 0 and the spin Hall being 1/2.
Yes, exactly.
Then how did you show this? Is this for some generic non-Abelian topological order with such symmetries?
So we have checked this for S being either U1 level 8 or Pfaffian or particle Hall Pfaffian or the 331 state. So all of the states proposed, then this is true. But we cannot guarantee that this is true for all the possible topological orders compatible with the transport data. But all the candidate ones, all the ones that have been proposed, this is true. But there may be some deeper reasons that this may be true in general.
Thank you.
Okay, so once we have these gap boundaries, we can build topologically protected qudits with this annulus geometry. So if we consider fractional quantum spin Hall state on an annulus with the inner and outer boundaries gapped out by some anion condensation, and the ground state degeneracy can be computed by this formula, which is dimension of the endomorphism of the algebra. And so using this formula, we can compute, for example, so in this table, I'm considering superconducting inner and outer boundaries for the candidate states. And so the annulus ground state degeneracy is 6 for Pfaffian times anti-Pfaffian, 6 for particle Hall Pfaffian times anti-particle Pfaffian, and 8 for U1 level 8 times U1 minus 8, and 4 for the Z4 order. So this shows that the annulus ground state degeneracy with gapped inner and outer boundaries can be used to partially distinguish these candidate orders, which could be useful experimentally to tell what kind of order we have in the system. So next, I want to discuss the twist defects in the fractional quantum spin Hall states. So first of all,
so when you said the ground state degeneracy can be used to distinguish the candidate orders, but experimentally, how does one measure the ground state degeneracy?
Yes, so that's a very good question. So it is actually possible to measure ground state degeneracy as people have proposed schemes for measuring ground state, like torus ground state degeneracy, which I will discuss later. So you can essentially measure the entropy of the system. And at very low temperature, the entropy should be log to the ground state degeneracy.
Thanks.
So next, I want to discuss the boundary twist effects. So let us again take the Z4 order as an example. So here I'm showing a Z4 order with 3 types of boundaries here. And so for instance, at this top vertex here, a domain wall between the E condensed boundary and the M condensed boundary. So there is actually a Z4 parafermionic mode with quantum dimension 2. And at this left corner here, a domain between the superconducting boundary and this superconducting plus FSA boundary is actually a Majorana mode with the quantum dimension square root of 2. And similarly, at this right corner, we have a Majorana mode with quantum dimension square root of 2. So we only have these three gap boundaries for the fourth order. So we only have these three types of twist defects in the fourth order. And because of this relation that we just discussed, so the boundary twist defects of all the other candidate fractional component spin Hall orders are actually the same as those of the fourth order. So which basically means this diagram, this triangle diagram, is true for all the other candidate fractional spin Hall states as well. Okay. So here is something that may answer Liu Jun's question. So we propose that it's actually possible to measure the Gromsey degeneracy by an entropic measurement. So if we consider this Adams geometry again, and if we so for this geometry we have fourfold Gromsey degeneracy, and if we apply out of plane electric field in this region A, and when the electric field is large enough, this region can be trivialized, and then the remaining region is essentially a disk. So it will have zero Gromsey degeneracy. And through the Maxwell relation, we can turn the entropy into polarization, right? So if we can measure polarization, and people have measured polarization in these twisted TMD materials. And if we measure that and do the differential with respect to temperature and integrate with respect to the electric field, then this should be approximately log of Gromsey degeneracy with some exponential correction that is suppressed when the temperature is low enough. And delta here is the bulk gap of the system. So here is so we did numerical simulation of this entropy measurement. So we only focus on the Z4 order because we have a Luniger liquid description of this Z4 order. And so if we add the proximity induced superconducting pairing term and also the electric field induced inter-edge tunneling term, and so we don't know the exact dependence of the coefficient on the electric field, but we only care about when the electric field is large enough so that the topological order is trivialized. And so the interaction matrix here is constrained by the symmetry to take this form 1 minus G sigma Z. So there's only one parameter G here. And so lambda S is the strength of the superconducting pairing term. And gamma is the strength of the field-induced inter-edge tunneling term. And S equals 1, 2, it labels the inner and outer edge. So this is the setup. And so when the superconducting pairing term is strong enough, the field phi E here will be pinned to a minimum. And so this means suppose the inner and outer edge field phi E are pinned to one of the four minimums, but we don't have 16-fold Gromsey degeneracy because we have the global constraint that the total system has net zero charge, which means if the fractional charge on the inner edge is 1 force, then on the outer edge the charge must be 3 force, or negative 1 force up to integer charge. So the actual fourth order.
I think I forgot about the notations. So phi E1 minus phi E2 is something local?
It is not something local, so you cannot pin this term to, but it is a anion tunneling operator. It basically tunnels the anion.
If it's not local, why can you write it in the Hamiltonian? Do you need to multiply it by some factor like 4?
I think this term is allowed when this term is large enough, because it's like if E is condensed here and here, then you can consider the Wilson line that join these two boundaries, and this line will not create anything, so it is a local operator. If the E particle is condensed on the inner and outer edge, when lambda S is large enough.
So this is assuming that the superconducting region is big enough so that the thickness of the gray area is small. So basically, yes. I think according to what you said, the support of this term is basically the thickness of the gray area.
Yes, that's correct.
Okay, thanks.
Yes, so this can basically be viewed as like Wilson line operator joining these two these two edges, and this is allowed if the E anion is condensed. Okay, so these are these states labeled by N is actually it's the actual 4-4 ground states. So it's a combination of states with these two fields appealing to fixed minima, and so that this state has net zero charge. So if we perturb above this this ground state, and if we only keep terms up to quadratic terms, then if we further discretize the circumference of this annulus, that is interval from 0 to A with periodic boundary condition, and then you can basically write this Hamiltonian as a collection of harmonic oscillators, which means we can compute the thermal entropy numerically. And so here is the result. So we compute the thermal entropy for a very small gamma zero. So because in reality, gamma, the tunneling may never be actually zero. So we consider very small gamma zero and then a very large gamma. So the little gamma here is a combination. So gamma is a tunneling strength, and L is the size of the region A, and lambda S is the strength of the superconducting perimeter. So if we, for instance, if you focus on this blue curve here, where this gamma is large, so we have this plateau of this entropy difference that is roughly log 4. So this is because when the temperature is low enough, then this S gamma 0 will essentially contribute a log 4. But for this S gamma, it will not contribute anything, because if temperature is low enough, the excited states will not contribute, and the ground states are lifted. The degeneracy is lifted when gamma is large enough. So we observe this plateau of log 4 for a range of temperature. And so we expect this to be true for other fractional quantum spin states as well. But for those, for instance, for the non-Abelian orders, we do not have a very nice edge theory to do numerical simulation, but we believe similar behavior should still be true for the other fractional quantum spin states. Okay.
Can I ask what exactly is the simulation that you did?
So the simulation is essentially simulation with Hamiltonian. This Hamiltonian is now a free theory, and it's a free theory. And so, and also, if we discretize 0 L, this interval, basically replace this by sum, and this is just a collection of harmonic oscillator, and it can be the eigenvalues can be found exactly, right? So then we can compute the thermal entropy. Actually, we apply the formula for the thermal entropy of harmonic oscillators, but this can be basically the thermal entropy can be computed numerically if we discretize this interval 0 L into 100 points. I think that's what we did, or 200 points.
I see.
Yes.
Also, I want to further comment on this interaction cosine phi E1 minus phi E2. It's the Wilson-Lang operator. I think you did mention you used the condition that E is condensed here, but I think this condition is used to say that this interaction will induce some low energy effect. I think even if suppose the superconducting region is big enough so that the thickness of the gray area is small, then no matter whether E is condensed or not on the boundary, I can just write down this term. But if E is not condensed, then this term is acting on some gap degree freedom. It doesn't have too many effects on the knowledge physics. I think the condition where E is condensed is used to argue that it has strong effects on the knowledge physics. But to say it's a local interaction, the condition is that the thickness of the gray area is small. Am I understanding correctly?
I don't think the thickness of the gray area is small is important. I think what is important is that this term, like this Wilson, does not generate any excitations on the boundaries.
Yeah, but if the thickness is big, then if I just write down the Wilson-Lang operator, that operator is supported along the Wilson line, which has a length proportional to the thickness. this thickness in principle can be infinite in the thermodynamic limit. Then it's non-local.
I see. So okay. I think I understand your point. So you are saying that this looks like a local term, but actually, so this I see. Yes, I think this is taken in the limit where the thickness is very small. So you can essentially view these two edges as being very close to each other. So it's like just 1D system. It's like essentially a 1D system. Yes.
Yeah.
Okay, thanks for this question. Okay, so allow me to discuss the outlook of this work. So I think this experimental observation of fractional quantum spin Hall state opens up the possibility of studying boundary physics in fractional quantum spin Hall states. For instance, so previously many experiments have studied the gapless chiral edge modes, but now it is actually possible to study gap boundaries in these non-chiral states and to detect the topological degeneracy. And also, it is also possible to study the boundary topological phase transition. For instance, for the Z4 order, or for any of these fractional spin Hall order, the transition from the superconducting boundary to the IVC boundary would be a deconfined quantum critical point, because this is two gap states with different symmetries, and a direct transition would be a deconfined quantum critical point. And it also opens up the possibility of realizing anion condensation in real world. So the theory of anion condensation has been established for roughly a decade, and now we have the chance of actually realizing it. For instance, we can experimentally study the transition from Pfaffin times anti-Pfaffin to the Z4 order. And also, it is possible to study the storage and manipulation of quantum information in gap boundaries. So we have shown that it is possible to build topologically protected qudits in these systems with gap boundaries. But the next step would be to engineer logical gates and do actual quantum error correcting computation in these systems. And that concludes my talk. And thanks very much for your attention.
Thank you for the very nice talk, very impressive. Any questions from the audience?
Yeah, thank you for the nice talk. So you talked about the boundary defects of the Z4 order. So do they play a role in the story? I did not see.
So it did not play much role in the sense that we mostly consider the qudits coming from the gap boundaries, not coming from these twist defects. But
yeah.
It is also possible to have a topologically protected degeneracy by building these twist defects, right? So if you have an array of like alternative boundary conditions, like you have superconducting to IVC to superconducting, so you can have a large topologically protected ground degeneracy. But what's difficult, what's the difficulty with this proposal is that it is unclear how one can perform any quantum gates on this degrees of freedom. But for the qudits associated with gap boundaries, there are at least certain gates that you can consider doing that. For instance, you can consider applying magnetic field, which can essentially do so recall that the M particle is charged under U1. So if we apply a magnetic field and increase that from 0 to 2 pi, it can essentially braid this M anion around. So it can serve as a gate, or you can try to braid. You can braid these holes, right? If you have two of these holes, and you can braid them, and that can also be a gate. But if you consider this twist defect, the question is, it is unclear that how one can use them to do anything.
I see. I think maybe for some topological order, one can use the so-called half-link. That is, you create a condensed anion on one boundary and let it move in a bulk, and then let it condense on the another side of boundary. Then it will generate a unitary transformation. But I don't know if in this case this is possible. So is it how can we realize such a defect on the boundary junction in experiment?
So I think as long as you can introduce superconductivity and intervalley coherent state on like different regions of the boundary, then you have this defect. So this is like, I think this region, like it may not actually be a point, it could be a region, but it is robust because like it does not have to be accurately like a point.
I see. Thanks.
So basically, you mean in different regions of the boundary, maybe in one region you can take some superconductor and do some proximity effect, and in some other region you take some other material that has IBC order?
Yes. For IBC order, actually, I think it's possible to induce IBC order with in-plane magnetic field. So if you apply in-plane magnetic field in this region, and then you use the conductivity proximity effect on this side, then actually to this region it does not have to be like actually a point. So if it's not a point, so as long as the region is small enough so that the separation of the of the topologically predicted ground states and the other excited states is large enough, right? So there are some exponentially degenerated ground states and there are some other excited states. As long as this gap is large enough, then we can use this as a quantum ring.
I have another question. At the end, you said it opens the way to store and manipulate quantum information in gapped boundaries. I want to ask, how exactly should one do it? You briefly mentioned if I thread some flux, then it will induce some Wilson loop for some of the anyons. Yeah. So what's the can you say? So besides threading flux, what else can one do?
You can consider breeding these holes. So if you consider, okay, maybe I have one figure in the first page. So if you have many of these holes, you can consider breeding them. You move one of these holes across the other, and this can also serve as a gate, as a logical gate. But this may have some experimental challenges because you want to avoid generating excitations that could be an error.
Also, usually in the experimental platform, you cannot move the holes, right?
So what you can do is you can try to grow the hole and then shrink it. So it's effectively moving it. So that's actually the proposed in the surface code paper, but that's not experiment. That's like IS model study. But what you can do is to try to grow this hole. Like if this you can try to increase this region of superconductivity and then try to shrink it on this side, and then you can gradually move it.
This needs to be done, for example, experimentally. If I want to do it, I want to put another superconductor to use the proximity effect to create the hole and then change the its side and move it.
Yes, I think that could work. Or you can actually just gradually move your superconductor slow enough, and that will actually move the region.
By moving the superconductor, you mean the superconductor from the outside that is used to induce the proximity effect.
Yes.
Yeah. Any other questions? Okay, if not, let's thank Ray for this wonderful talk. Thank you.
Thank you very much for your attention. Okay.
Yeah, bye.
Bye, everyone.